Vamos a,
Noted.
vamos a comenzar. Okay, so we'll start. So thank you very much to the organizers. Of course, I will be chairman of the first two sessions. And here on the you can see the rules for the sessions. And our first speaker is Tomas Andrade from Universidad de Barcelona, who will talk about numerical aspects in GR and holography, I guess. So thank you, Tomas.
Great. All right. Let me try to share my screen. Can you see it?
Yes.
All right.
Hey.
All right. So here we go. Yeah, I'd like to start thanking the organizers for giving me the opportunity to present this for everyone. It's been super fun preparing for this. It's also a difficult challenge because it was somewhere in between a colloquium and a technical talk. So I wasn't very sure on how to approach it. But at some point, Carlos told me, well, imagine you're going to start working with someone. What would you like to tell them? What would you like them to know before they start working with you? And that was really, really a nice approach to start preparing for this. So hopefully you will enjoy it. I have to say that I will need your help to make this more entertaining as well. If you have any questions, please interrupt me at any point. I'll try to answer the question rather well, either at the moment or at the very end, or maybe if the question is too complicated, we'll save it for the discussion session in the end. Right. So, whoops. I was also asked to state my commitments, my goals at the very beginning. So here's my goal. It's a very ambitious one, just to motivate you to think about general relativity in a dynamical way. So this is my goal. My dream is to inspire you to think about GR dynamically, but maybe that's too much. So I would motivate. I will be happy with that. And why is that? It's because this hopefully will help you expand your intuition about general relativity. And here I have to make a personal confession that this really helped me breaking some sort of mental block that I had when thinking about black holes, for example. So whenever I would write the Schwarzschild metric, I would imagine this sort of cathedral or a sphinx or this, like huge thing that is like always there forever. It's not allowed to move very much. And that really was like giving me a mental block to try to think about general relativity in maybe a slightly more profound way. If you're anything like me, maybe you're also feeling this way. And trying to think about general relativity in a dynamic way will help you expand your intuition about it. And you can start thinking about other more interesting phenomena. I don't know why, no, what's that stuff? So the means to an end will be to show the very, very basics in a simple example. I will tell you in a moment what that will be. I'm sorry to disappoint you if you're hoping to see the full bells and whistles of numerical GR. You won't be really seeing that here because I think that's too complicated, and for a 45-minute lecture, that wouldn't really work very well. But hopefully you'll begin to see the sort of walking skeleton version of that in a simple example. Right. So just to continue with my motivation, hopefully you guys did your homework and read a little bit, at least part of this short story by Jorge Luis Borges called Tu Nugbar and Urbis Tertius. And here, what Borges is trying to portray is a world that doesn't have any nouns, that people don't really think in terms of nouns, of fixed objects, but in terms of verbs instead. And I think this might help you break that mental block if you have any. So let's read it together. Sorry, I'm just going to have to move this. Okay. So Borges says that for the people of this planet, the world is not really a mixture of objects in space, but instead it's a series of independent acts. So the world is successive, temporal, as opposed to being this more Aristotelian sort of version of objects that have an essence and do things. So here the emphasis is actually placed on the acts that these objects, or the acts that just happen. I don't know. So because of this, or maybe the other way around, because the language doesn't have nouns, or the conjectural, this funny word here, Ursprache means proto-language, this conjectural proto-language from which all the present-day languages derive, doesn't have any nouns in it. It only has impersonal verbs and some suffixes that modify them. So if this is not confusing enough, here's an example. And well, before what I censor here is that, well, Borges is saying that the word moon doesn't exist in this language. So if you want to say the moon rose above the river, well, you will obviously say Hlur u fang axaxasem slo. That's the phonetic translation of that. Or as someone translates upward behind the on-streaming, it mooned. So the word moon doesn't exist, but the verb mooned does exist. So when you first see this superficially, you're like, oh my God, this is really cool. There's no moon, but somehow there's a verb that replaces it. That's version number one. But version number two, you see that the word river, which for us is a noun, it is a noun also in the language of Slun. And that's really exciting the first time you read it, because like, oh my God, Borges made a mistake. And it's really cool when you catch other people's mistakes. But Piglia says that this is perfection and there are no mistakes in this short story. So you have to try to think a bit harder about it. And there are two things, well, a couple of things. So someone translated this phonetic thing, right? So maybe something got lost in translation. So Chul Solar, actually, Chul Solar is a real individual. If you go to Wikipedia, you'll find he's a linguist and a painter. And he, well, translated this, the sentence into, well, English, right? So, well, maybe I'm presenting this in English to you and you're like, well, but Borges obviously wrote it in Spanish first. But that's not the answer of the riddle either, because actually in the original Spanish version, the translation from Clunian to us is given in English as well. So that's not the that's not the end of it. And what the interpretation that I like the most is going back to the word Ursprache, which means proto-language. So that means that in the proto-language there were no nouns, but maybe in the present day languages some corruption happened and some nouns made it to the modern language. And maybe that's what happened, that the word on-streaming became a noun, whereas the word moon didn't make it, and we have to just use the verb. So anyways, I will definitely recommend you to go back to this text and read it. You'll find a lot of jewels in it. It's actually a really beautiful thing. To try to summarize the point that I'm trying to make, this is Rio Calle Calle, if you know that famous Chilean song. So instead of thinking about objects, think about acts. Instead of thinking about nature, which is a past participle for being born, try to think of the Greek equivalent, which is physis, which is more or less a translation of a verb, which is to develop. And our dynamical equations, particularly of general relativity, have time derivatives in them. So this process of change, of constant change, is actually something that is embedded here. And maybe just by thinking about relativity and specifically about simulations and relativity, you can start trying to imagine how the world of Tlun might evolve. Right, so I would love to just stop here, but you probably want your money back if I did. So let me just dive a little bit into the more details of this. So I'm going to show you 4 different projects that you can approach by thinking about general relativity in a dynamical way. The first one is directly related to holography. So here we see ADS, right? This is the bulk of ADS. Here's the holographic coordinate. I'm going to be very sketchy because this is still part of the motivation. And what we usually do here is to specify some initial conditions at the boundary. So imagine this as some sort of lumps of energy with some given momentum that will set this in motion. And then by solving the equations of general relativity, we will see how these lumps of energy evolve. Of course, because we're doing holography, we have to also solve the gravitational theory everywhere in the bulk. But in the end, our main objective is to extract what the properties of the boundary theory are. And this is something that thinking about GR dynamically will allow you to do. So for example, people have thought about connecting this to to dynamics of QCD, for example, if you've been following that sort of literature. So that's one kind of project. There's another kind of project that essentially you can think about by just solving the radial dynamics here, just integrating out this radial direction, just solving those equations once and for all. And you can do that in some approximations. So in the fluid gravity limit, where all the momenta are much smaller than the temperature scale, you can use this approximation to fully integrate out the radial direction here, to completely forget about it and write down an effective theory that only cares about the boundary or the horizon. A similar approximation ensues if you take the limit of the dimensions of space-time going to infinity. This is actually very similar. And you can, the point is that in some nice regimes, you can forget about the bulk and just get a theory that lives on the boundary or the horizon. In some cases, I will discuss this in a little bit of detail later, this movement of lumps on a brain approximate quite well the dynamics of now compact spherical black holes in a large limit of, in the limit of large limit of large spacetime dimensions. So instead of these blobs, you can think about black holes, and in some cases, they end up being very similar. But now that we're at it, and if our code, we're taking D to be 8 or 7 or 6, we can equally well take it to be 4 and study collisions of black holes in 4 dimensions and throw some interferometer there and extract the waveforms that these collisions produce. And this simulation is very relevant to observations, because if you want to detect the gravitational wave, you really need to know what to expect. So these are 4 projects that you can work on by thinking about GR dynamically. And today I will, because of mathematical simplicity, I will focus on this one here that I will call blobology. So there's a paper that came out recently that calls this blobology, and I will tell you why. Hopefully, this will be a good toy model for the whole shebang of GR in a dynamical set. Let me just look at the time. Okay, so we're good. So here's the outline of my talk. I will first derive for you the effective theory of the blobs. I will discuss some of the nouns, some of the stationary solutions that live in this theory. We will also discuss, and this is going to be where we're going to spend most of the time, thinking about dynamics, how to model the dynamics of this theory. And if time permits, I will show you an application at the very end. So, okay, let's get started with the effective theory, and I'm going to need a whiteboard. So I'm going to change the background a little bit. This is the most equation intensive slide, this one and the next. So if you don't like equations very much, if you think that you want to do something else, please go ahead. I won't feel offended. I'll wake you up when we go back to simulations. But I think it's a good grounding point to write some equations down, especially if these are equations that we all are very familiar with. So we're going to start with the action. So it's a good starting point to write down the action. This is just the Einstein-Hilbert action with the cosmological constant in capital D number of dimensions. And we're going to, the first thing we're going to do is to split this capital D, split the coordinates into n, little n, p, and 2. So we're going to split the coordinates in three kinds. Let me write the ansatz for you. This is a black brane ansatz. This is the line element that has the coordinates t, r, x, and this is blocking, and y. These are the 3 groups of coordinates. So tr are in here. The n's are these y's, and the p's are the x's. There are some arbitrary functions here, a, fi, gij, and gperp. And these are arbitrary functions for now of all coordinates except for these. So there's some symmetry we're assuming here. So the active coordinates are these, and there are some like passive coordinates that don't really matter that much. This entails assuming some symmetry assumptions. So we have p of these x coordinates, and n of these y coordinates. And we're going to Kaluza-Klein reduce over these coordinates here. So what does that mean? Essentially, we're just going to write down the full equations of motion, assuming that nothing depends on these coordinates here. So what you're going to get is a reduced theory of gravity coupled to a scalar field, and the scalar field, the role of the scalar field played by this guy, G-per. So there's some calculation to do here, but you can easily write down the equations of motion, and after that, you end up with a theory that lives in this p plus 2 dimensions that you can easily play with in Mathematica, for example. After you do that, we're going to expand now in 1 over n. So all matrix functions will have some expansion in 1 over n. So note that taking n to infinity is like taking d to infinity, but we need to keep some things fixed. And the things that we're going to keep fixed are the number of active dimensions p and this radial coordinate r to the n, just that. So whenever you take a limit, something going to infinity or to 0, you need to decide how you're going to scale things. And the way to organize that is by keeping these quantities fixed. Good. Hopefully you're still with me, the ones that want to remain with me. And this is what we're going to do. So we're going to expand all these functions in 1 over n, plug them into Einstein's equations. And this is what we're going to find. We need to solve order by order in 1 over n, remember that. So we can actually solve a lot of the equations that come out of this. You can solve the equations that involve the coordinate r. So all these leading coefficients here that involve functions of r, these are outcomes of the equations of motion. You also get, obviously, some subleading terms. But for now, the only thing that we care about are the leading order coefficients. So this y here, no, this is a typo. These are just x's. Yeah, you can have more than one x, but not any of these y's here. Maybe this is bad notation. We're going to get that and some constraints. Some constraints for these free functions here that I colored in red. And if you're wondering what these quantities are, well, these are precisely the energy or the mass density of the brane and the momentum density of the brane. So if you're thinking about ADS-CFT, for example, these are precisely the components of the stress energy tensor. If you just look at the metric, the 1 over r to the n, that's precisely where these coefficients show up. So, well, we have this expansion, and m and p are not fully arbitrary. They satisfy some constraints. And those constraints are precisely the effective equations of the theory. So let me write them down for you. They're very, very simple, very short. They look like this. So these are essentially non-relativistic hydrodynamic equations. So if you look at them, they're essentially some diffusion equations. So you have 1 temporal derivative, 2 spatial derivatives here, plus some corrections. They end up being non-relativistic because of the way you scale things. So you're taking essentially the limit of the speed of light going to infinity. That's why they have this non-relativistic structure to them. But you see that they're very, very simple to work with. But they still capture some very interesting physics. Before we say anything else, let me just emphasize something that you would never know if I don't tell you, because this is like a very detailed thing. But this sign here has 2 possibilities. It can be a plus or raise hand. Sorry, just Julio, go ahead.
Hello. So, Tomas, the non-relativistic limit has something to do with the large d?
Well, yes and no. So in this case, in this particular limit, I end up having a non-relativistic limit, but there are other limits that are not non-relativistic. Okay. So this particular limit that I'm taking ends up giving you some non-relativistic hydro, but it's not unique.
So in principle, if you do this in finite d, you would obtain also a non-relativistic equation? Is it?
I don't know what you mean here. I'm literally taking d to infinity.
Okay.
Finite n, I think is.
Yeah, dimension. Okay, thank you.
Yeah, is that okay? Andres?
Andres.
Andres?
You have to unmute. You have to unmute.
Good. I think this is due because the answer is R is null. And when you reduce over a null coordinate, you get something like it's non-relativistic.
Why are you saying it's null?
Because in the answer there is, I remember that
There was no dr
it was
square.
not dr square.
Right, was dtdr.
It's
Yeah,
the dr and the t square, and there is no dr square. So then r is null. It's a null coordinate.
Yeah, well, we can talk about it at the end.
Okay.
I don't remember. Maybe there's a typo there, but yeah, I don't remember r being null. R is essentially just the usual radial coordinate.
May I ask you one more? Sorry that I don't have the raised hand here.
No worries.
So why we got here one time derivative, given that the original equations, where is it's in the limit, how it comes up?
Right, yeah. Let me try to write this down here. Right, 1 sec. So we're comparing the x's. Something to do with the scaling of x being different to the scaling of t. That gives you a notion of the speed of light, and you're taking that to be infinite.
I see.
Yeah, it's because of the scaling. So as I was saying before, you can take different 1/d scalings and then take this little n to infinity, and you will get stuff that is actually relativistic. So people have also done that.
One more, if you want, postpone me for the discussion. When you take the number of y coordinates to be very, very large, right? Aren't we putting there infinite volume? So aren't we compactifying on a manifold of infinite volume just because there are so many of them, even if each one of them is compact?
Infinite volume. Well, I guess you're always going to divide by that volume in your physical quantity. So yeah, if you have an infinite brain, you have infinite volumes, but
constant going very small because it's going to be divided by that.
Well, this guy here, you mean? Yeah, could be that.
Good. Okay. We could discuss more in the discussion.
Sure. Yeah. So yeah, thank you. So this sign here, as I was saying, so there are two possibilities for this sign. So if you considering an asymptotically flat brain, this sign will be positive. If you're considering an asymptotic ADS brain, this sign will be negative. And this has important consequences for the dispersion relation of the modes around the homogeneous solution. So in the case of the plus of asymptotically flat, you get the Gregory-Laflamme instability of black brains. And in the case of ADS and the minus sign, you just get the standard sound and shear dispersion relations for hydromodes in ADS brains. Right, so these are the equations. These are the equations that we're going to solve, and everything we say from this point on will be referring back to these equations. As you can see, are very simple. So we're going to look at some stationary solutions of this set of equations. The first type is what we've been calling blobs. That's what gives the name to the example. There's another kind of analytic solution. These are both analytic solutions. These are we call bars. And the blobs are just blobs. This is a Gaussian profile in M. And the profile for P is just a derivative of M. If you plug that into the equations of motion, you get that this is a stationary solution. Good. In the case of the bar, this is essentially an oblong Gaussian that has some width in one direction, some width in the other direction, and rotates with constant speed. These are both analytic solutions of the theory. What's very interesting is that these blobs mimic very well at least the near equilibrium dynamics of Myers-Berry rotating black holes, in the sense that if you compute the quasi-normal modes within this theory of these blobs, you get a really good approximation to the quasi-normal modes of the Myers-Berry solution, also in the large D approximation. So this is cool. You can think of blobs as Myers-Berry black holes, at least in this sense. One of the unstable modes of the blobs are dipole deformations. And if you follow this dipole deformation non-linearly, you'll find this solution. So typically, this is something that is very hard to do. So when you find an instability, you usually don't know what's the endpoint. But here you can do this non-linearly. And you can construct the solution fully non-linearly, just starting from the instability. These bar solutions are themselves unstable if they're too long and thin. Essentially, again, a version of Gregory-Laflamme that is at play here.
Thomas?
Yes.
When you refer to Myers-Berry, is the spherically symmetric or
yes.
is a sort of planar?
No, the spherically symmetric one.
Okay.
Yeah, thanks for the question. So maybe a little bit extra piece of intuition. If you take the Myers-Berry black hole, let's say when one angular momentum, and you take the sum of that geometry to the North Pole, that geometry coincides mathematically with the geometry that you get from this. So if you remember that these equations come from an ansatz, if you go back to that ansatz and plug this configuration in, you will see that geometrically there's a region of the Myers-Berry that is captured by this blob, and that will explain why you're getting some of the physics right. I don't know if that helps. Okay, so we have this stationary solutions that we can start building our intuition from with them. We can study their quasi-normal modes, so they're near equilibrium dynamics. This is done in the usual way. So imagine we only have two coordinates. In space, we have r and phi plus the t coordinate. So after we find this spherically symmetric solution, like the blob, for example, this is a background, and we expand around this background, assuming some harmonic time and angular dependence, plus some time profile that depends only on r. And then we keep up to leading order in this deltas. You obviously have to do the same thing for the p's. This is the standard way of solving for quasi-normal modes, just doing a linear calculation with some frequency dependence and some angular dependence. The goal of that calculation is to find omega as a function of m and the rest of the parameters of the theory. So maybe remarkably, in this case, you can also do this calculation analytically, and you can find this dispersion relation, this quasi-normal modes, fully analytically as a function of m and the rest of the parameters of the theory. And an interesting question then is, well, remember that these solutions are always complex. So asking for linear stability corresponds to asking if there are any modes that jump into the upper half of the complex plane. And why is that? Because if the imaginary part of omega is positive, you have exponential growth of some modes. And well, in some cases, you do find such instabilities, both for the black holes and the bars. And then the interesting question is, and something that is usually very, very hard to answer in GR, but here it's not that hard, is what is the endpoint of these instabilities? You have lots of these, and here you can study in this theory after you kick in those unstable modes where the solutions want to go to. Right. So that's just to start warming up and building some intuition, but now we're going to discuss the nitty-gritty of the numerical evolution of the theory, because the equations are simple, but not simple enough that we can find everything, absolutely everything analytically. So the first thing that you need to do is to discretize space. What do I mean by that? So we have these equations, right? They're very nice. It's dt equals something. We need to decide the grid that we're going to use to approximate all these points. So these are all functions of two coordinates, let's say, for simplicity. So we have a grid, and we're replacing this continuous function m for the values of that function at all the nodes of this grid. So instead of m of x comma y, we have m of ij, so a discrete set of points with some time derivatives at each point. We have degrees of freedom sitting at each of these points. And now we look at the right-hand side, and the right-hand side has derivatives. And taking a derivative essentially means to connect each point to the neighboring points. Here, this Laplacian, that's precisely what it does. And a lot of the hard work goes actually into estimating these derivatives. There are many ways to do it, but the simplest one is to consider nearest neighbors, and precisely this Laplacian is what this is doing, and the nearest neighbor approximation of the Laplacian is just connecting the central point to the same point and just the nearest neighbors. And you have to do the same thing for P's as well. But this is very simple. After you've done this, you've reduced the system to just a bunch of coupled discrete equations. So after you do this for the M's and the P's, you have some gigantic vector or matrix of however you want to do your bookkeeping. Y, the time derivative of that, equals some function of all the Y's. So function of all these points. And after you've done that, well, you have to just solve this equation. And you need to do two things to solve these equations. You need to specify an initial condition, and then you simply need to do the time integration loop to get your evolution. So let me show you how we do that in some detail. So first, we construct initial data, essentially, again, by discretizing our grid. And here what we're doing is translating this idea of, well, we have two blobs that want to collide with each other. That's some expression for the M's and the P's. And just for simplicity here, I'm going to imagine just I have one blob, one Gaussian blob with some width. And remember that I've decided to discretize the X's and the Y's in some grid. And this is what I get, right? So M of ij, at t equals 0 is a discretized version of the blob. So it's the values of the points, the values of this function at each of the grid points. I also need to discretize the right-hand side. So I need to evaluate these derivatives in some discrete way. It's typically some matrix multiplication. And I can just evaluate the right-hand side by acting with this now matrix derivatives onto this set of points. So I can construct this, and this gives me immediately this. Again, there might be some extra work to do this, but I guess the idea is very clear. So you start with a discrete version of the initial data, and then you evaluate the discrete version of the right-hand side at t equals 0. So in this theory, because we've solved all the constraints, there's no residual gauge symmetry. Any set of initial data that we specify is going to give you a well-defined evolution. It might be more or less interesting, but it's always going to be well-defined. In the case of GR or other gauge theories, not any set of initial data is equally good. Only the sets of initial data that solve the constraints of the theory are good initial data. And you need to solve some static, some elliptic set of equations to find out exactly what that can be. So this is a big difference between our setting and full numerical GR. Good. But provided you're able to do that, now you can just do your time evolution. Remember, we just have a bunch of degrees of freedom that are coupled to each other in this way. And well, the simplest way of visualizing this is just by expanding to leading order this derivative, and you get this, right? You get y evaluated at t plus dt is equal to y to t, y at t, plus dt multiplied by f. So if I know y at t, I can update it by simply evaluating this f of y. Of course, we need to do this in a discrete way. So dt needs to become a discrete number. And this becomes more explicitly the I plus 1 update of your of your evolution is the one in the past plus this combination here. And well, now you just need to throw in a for loop. You do this until you want, until you get bored, or until your code crashes. But there's one important point to keep in mind, is that depending on how you choose to discretize space, your discretization of time is bounded. You cannot have arbitrary precision in time given your precision in space. This exact bound depends on the system, but it's important to keep in mind that you cannot discretize these two independently. Great. After you've done all the work, so you set up an initial condition, you're able to cook up your loop of time evolutions, you're going to get something like this. So you're going to have these two blobs set in collision course, and they collide, and then they form a bar in this case, for example. And one thing you'd like to know is, after all this hard work, what are the properties of this bar that you found? So you need to extract the parameters of your simulation, of your final state, for example. So here, what you can do is to go to the center of mass and look at the principal axis of this bar, and then do a fit. So the points are the numerics, the lines are some fit. And by doing this, you can extract the properties of this. So if you have, for example, in the case of full GR, you'll have a final black hole and you'd like to know the mass and the spin. And you'll do something very similar. You need to do some fit to your numerics to extract the physical parameters. Another type of post-processing you'll be interested in doing is doing some kind of integrals at infinity that will allow you to extract gravitational waves, for example, or total mass or the total angular momentum, depending on the theory you're looking at. So these are two types of post-processing that you can do after all your hard work solving for your numerics. Let me just look at the time. Okay, good. So, well, some people were omitted from this talk, some aspects that are essential part of numerical GR that are not part of this theory, that these are part of the simplifications that I mentioned before. One of them was the fact that to find good initial data, you need to solve the constraints. So there are other two technical aspects that are worth mentioning. One of them is called AMR. This means adaptive mesh refinement. Let me just show you a picture that I think will be very clarifying. So you need to resolve some gradients, typically. You need to resolve some length scales. It's very expensive to increase the resolution of your simulations everywhere at the same time. So here you have some, really tiny separation when the gradients are large. It doesn't matter what this means. But you see that you don't need to do this high resolution everywhere. You need to do it in a way that is smart enough that you can just resolve the gradients that you want without making the simulation absurdly expensive, right? And this is an essential part of many of these simulations, but in the case of the blobs, because things are relatively simple, you don't really need to do this. This is something that if you do numerical GR, you need to worry about. Or at least someone needed to worry about this because there are now some nice software packages that do it for you. But this is always part of the game, one way or another. Well, something else, usually because of this, these are very data intensive applications. You need some sort of cluster or supercomputer to solve the actual linear equations for you. This is getting smaller and smaller, but for expensive problems, you really need a supercomputer. So let me discuss an application very briefly, which is horizon pinching. So imagine that we're colliding these two blobs, and we know that some bars can be unstable to Gregory Laflamme. So if we collide two blobs in a way that the bar that we form is unstable, what we're going to see is that we form a horizon, that the horizon then pinches off. So here's what it is. So you see that there's a bar that forms, but that bar is somehow too long. That is unstable to breaking apart, so you can figure that out linearly. But then the simulation tells you that this keeps going and the blobs just fly apart from each other. Here, that's all great, but I'm cheating because this effective theory ceases to be valid when that happens. But just to trick your mind, I just show you that. So we did this simple simulation with the blobs. And now the interesting question was, what happens if you collide actual compact black holes in not infinite dimensions, but sufficiently high dimensions? Do we get the same kind of behavior? And the answer was yes. It took us, well, 2 years to do that. And essentially, we're just solving Einstein's equations in the vacuum. There's nothing. I'm going to show you just a numerical relativity simulation now. We're solving these equations with this initial condition. I have just two black holes with some impact parameter and some spin. And well, there's a lot of technical details that I'm going to skip. So you have to choose a gauge. You have to implement your evolution. You have to then parallelize it. You have to do a dimensional reduction. but we use a software called grchumbo that does all of this nicely for us. And here's the result. So we have these two black holes that are set in collision course. They will collide, and then you'll see what happens. So you see an elongated horizon forming, and then the whole Gregory-Laflamme instability dynamics set in. So if you were to do something like this in a string, you will see this same satellite formation. But here we were able to arrive at this state by colliding two black holes. The simulation is in 7 dimensions, but in 6 dimensions, you see exactly the same thing. And this resembles very closely, this is not a simulation, this is an experiment with water falling off a faucet. This has been filmed at really high temporal resolution. And you see this stream of water pinching off. The onset of this is the Rayleigh instability that is actually very similar to Gregory-Laflamme. But this tube of water pinches off, and then molecular dynamics become important, this evaporation of this tiny drop of water. And the interesting question that we're trying to answer now is whether black holes break in exactly the same way as water does or not. So just let me recap. We discussed in some detail numerical evolution that involves a few things. So first of all, we have to discretize space and time. Well, and for GR, of course, at first we need to separate space-time. That is usually this one entity. You have to separate it doing an ADM decomposition. I didn't have time to discuss that either, but let's assume that you do that. And after you do that decomposition, you discretize space by turning your functions into discrete values. You have to evaluate derivatives, blah, 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 and then you do the time evolution also in a discrete way. You need to provide good initial data. And after that, you do a loop of time integrations to find the numerical evolution of the system. That was the main part of the talk. And then we briefly discussed an application involving the pinching off of a horizon and a black hole collision. And yeah, hopefully you're sufficiently motivated now to give it a try yourself. Thank you so much.
Julio, I think that you can unmute yourself.
Yeah, I think that's pretty close to 40 minutes. So go.
Okay, so let's have some questions. Let me see, Andres and Avalon, please go ahead.
So my question is, this is can be done in the sitter, the same kind of simulation?
The large D, or which part?
Well, the collision of black holes.
Yeah, sure.
So there is no technical problem to do these things in the sitter.
I don't think these simulations are very well developed. People are just now starting to work out the details of doing time evolution in anti-de Sitter. But in principle, there's no obstruction.
Okay. And it's just a question. I don't really know if this Gregory-Laflamme instability has been studied in the sitter. Do you know this? Not in anti-de Sitter, I know.
There's some work in ADS. Do you have strings in the sitter? That would be the place to start.
Okay. So I know that there is like in anti-de Sitter, the endpoint of the instability is an inhomogeneous string, right?
I think that's a dimension dependent statement.
Okay, well, thinking 5 to 4, something like this. But in the sitter, I don't know.
Yeah, what would be the starting point solution?
Well, okay, thank you.
Yep, thanks. Julio, I think your hand's still up.
Ahora sí, yeah. Sorry, so I wanted to ask a question. So are there conserved quantities in the evolution of the blobs system?
Yes, excellent question. Yes. I don't. Maybe I can share my screen again. Yeah, so let me show you the equations. Right. So definitely, yeah, if you take the integral of this, the right-hand side is a pure derivative. So you get for free that the integral of the mass and the momenta is conserved. Also, if you construct the angular momentum, so in 2 dimensions would be just xpy minus ypx, you can also show that that is conserved. But that is a largely artifact because you don't have radiation.
And in the simulation that you did, do you know that there is this critical dimension d equals 13.5 for the Gregory-Flam instability? So you did it in d equals 7, but are you thinking to go beyond 13, but still in finite dimension?
You mean the black hole collision? Yeah, that's something that we've thought about. There are some technical issues that if you go, say, above 10 dimensions, the numerics become really hard to do because the gradients are really steep. So resolving those gradients can be pretty hard, but yeah, something that we've considered. That maybe you can get, yeah, because of, as you say, if you do this in 14 dimensions, maybe the strings don't break. Maybe the strings become the snaps, the non-uniform black strings. Yeah, that's a good point.
And the last question is, whether does it make sense to solve the constraints perturbatively in 1/d, in a 1/d expansion? So does it make sense to know?
Well, I guess in this case, at least to d equals infinity, we did it, right? The constraints are fully solved, and you're left with equations that are unconstrained. There's no gauge symmetry left.
Can you study the first 1/d correction of that, for example?
Yeah, people have studied, I think, up to 4 1/d corrections in some cases.
Okay.
So yes, good to see you.
Hi, Tomas. Nice
Hola.
talk.
Thank you.
You are doing this in Wolfram language, or you are using Python or something else?
The blob simulations, I have a code in Python that I can share with you.
Okay.
A Mathematica code as well. But for the full numerical GR simulation, you cannot do any of that. You need to use some other kind of software.
Oh, okay. Thanks.
Yep.
And you want to study the gravitational waves using this, or okay?
Yeah. Well, for gravitational waves, I think the most developed one is called Einstein Toolkit, and I'm currently working on a project doing that.
Oh, right. Oh, okay.
Yeah, if you want, we can talk about that later.
Perfect.
Great.
Tomas, when you mentioned the thing about gravitational waves, what's exactly the thing that you can extract from the simulations, like the energy radiated, the shape of the waves, the spiraling, all of that you can take just by doing this integration at infinity?
Yep. You compute, usually what you do is to evaluate some gauge invariant quantities at infinity, those Weyl scalars. And from those Weyl scalars, you can reconstruct the total radiated energy or the waveforms or anything you want.
Okay, thanks.
Tomas, may I ask one? Sorry, I don't have the hand here. In this was very interesting, and if you wish, postpone me to the discussion later today. But in this phenomenon of the water pinching, the water falling, that you compare with the horizon forming, etc. So how the comparison goes is at the level of the differential equations. How you mentioned you are studying the problem. What do you compare to say it's the same phenomenon?
Right. So I can tell you what the progress that has been made is at the level of linear stability. The dispersion relation of the Rayleigh instability, it's very similar to the linear dispersion of Gregory-Laflamme. That's one thing. But then if you go fully nonlinear, if you are approaching the pinch off, in the case of hydrodynamic equations, you know that there's an analytic solution that allows you to continue over the pinching. There's an attractor solution that is well known in that case. And that's one of the things that we would like to know, if there's an attractor solution here. So there hasn't been a lot of progress on that directly. There's another interesting point that for some low viscosity fluids, you have the satellite formation. And we know that gravity is the lowest, or black holes are the lowest viscosity fluids in the universe. We would expect that that's also the case.
What you mean by satellite formation?
Yeah, so there's little beads that form.
Oh, okay.
People call those satellites.
Okay.
So this goes back to 2010, work by Luis Liner and Franz Pretorius. They did this, and they studied the formation of the satellites, and they said, well, this is self-similar. That if you have a string that breaks into two, then that little string breaks again into two, and so on and so forth. And they made the claim that there's some self-similarity there, and we're trying to study that in a little bit more detail. Because in some fluids, you also see that.
I see. Thank you.
So we're trying to come up with some sort of unifying theme here. So when water streams break, we know that there's some molecular dynamics that are taking care of the pinching off. And here that would be quantum gravity, essentially, that is evaporating that quantum.
Okay, okay. This molecular dynamics will not be captured by the hydrodynamics, right?
Well, no, the answer is no, but because of this attractor, they're unnecessary.
Mm-hmm.
That's the answer.
I see.
Mm-hmm.
Thank you very much.
Yep, great. Julio? Julio, your hand is up. I don't know if you're trying to ask a question.
Yes, so yeah, I was not unable to unmute myself,
All
but
right.
now I can. So,
Sure.
So in the pinching off, do you expect to have some corrections due to higher curvature contributions, or those wouldn't affect the dynamics?
Yeah, that's a really good point. That's related to what we were just talking with Carlos. If there's some sort of quantum gravity kicking in, and if there's an attractor, I guess the answer would be no. Because in the case of water, what you see is that you can match the experiments very well just using the attractor solution without having to worry about molecular dynamics there. If the same holds true in gravity, then you don't really need to worry about these quantum corrections.
Great, okay, if there are no more questions,